Hello, now in this video we will discuss equilibrium Green's functions. Equilibrium Green's functions. So then the Green's function is the basic object in response theory. So and the Green's function tells me if or how a system will respond to a impulse. So in some other context, the Green's function is also called the impulse response. So Green's function is as well called an impulse response. And then this impulse response tells me if I introduce a perturbation in a system at time t. So perturbation at time t, and the Green's function will help me know or predict what will happen or what will be the response at a later time t prime. Basically, for this scheme, what we use is the following. So we use a contour, a drawing in black, and in this contour, which this is plus infinity and this is minus infinity in time, this is very important. This is a single-sided contour. So just pay attention here because we have double-sided contours. And it's crucial that you understand this. Okay, so then in this contour we have these two events, the perturbation and their response. Let's say that the perturbation is at this time t. Then we will observe a response at time t prime. And then what we want to calculate in quantum mechanics is the probability for this process to have place. Okay? What is the probability for, let's say, if I put an electron here in the system at time t, what is the probability to measure that electron again, let's say, at time t prime? See? This is what the Green's function does. It tells us the probability for a process to take place or for a process to undergo in a quantum mechanical system. And we will discuss that in a later video. So, and for the meantime, what we can say is that in this contour picture, what we have is that the Green's function can be defined in the following way. Let's say that your physical system has two different positions where the two different events happen. So they don't have to happen in the same position. So one can happen in the origin and the other can happen far away from the origin. And these two positions are labeled as I and J here. Then the contour Green's function, which is the Green's function that measures the probability amplitude for a process to trigger in the system depending on where the times, these times t and t prime, are on the contour, is given by this. It's called the contour Green's function because the probability amplitude for these processes to take place depend on the relative positions of the time instants in the contour that I just draw, which is important. Now, the definition of that Green's function is nothing but minus I over h bar. Okay, the expectation value of the time ordering of the time or the time order expectation value of second quantized operators ci of t and cj dagger of t prime. Okay, where we know already, we have discussed a little bit that this ci annihilates particles inside I, and this CJ dagger creates particles on side J. This is a single particle operator, so each of these operators just annihilates or creates a single particle respectively. Now let's talk about this operator T, time ordering operator. What the time ordering operator does is that takes into account, as I said, the relative position of the events in the time contour, whether the event happening at T is happening before T prime or happening after T prime, which is quite important. We will discuss that when we get to touch non-equilibrium Green's functions. But for the meantime, let's see how that time order operator is defined. So this is for T greater than T prime first. So we have to fulfill this condition. Then here we write theta of T minus T prime, Ci of T, Cj of T prime. Okay, so what that means is that if T is greater than T prime, whatever happens in T prime happens first, and then whatever happens at T happens later. So then what happens first goes always to the right, and what happens later goes always to the left, as is obvious from a contour. So in this case, in this contour, as I draw here, T prime is after, so what happens first is T. So then the time ordering operator puts everything that happens first to the right and everything that happens after to the left of that. So in this case, this first term here will be equivalent to something happening first here at T prime. Let's put it here, and something happening after that here at T. So this convention is not right for what I have written here. Now, the first convention that I had this at T here and later at T prime will be then something like this. So because we have to consider events, we have to consider the case for T greater than T prime, and we have to consider as well the case where T is less than T prime, which will be a reaction written as follows: theta of T prime minus T, Cj dagger of T prime, Ci of T. So what happens first goes to the right. See, here this T is happening first. Whatever is happening at T is happening before T prime, okay? And then something happens at T prime, so that reaction, which is labeled by a creation operator, goes to the left of Ci of T. So then what the time operator does, this T here, is that orders these operators according to the sequence of occurrence. Okay, so then that's what this operator does. We will not use that very much in this lecture, but we will have to have that present for the case of non-equilibrium Green's functions, which is a more advanced topic. For the meantime, we will not work with this contour Green's function, but we will work with the classical Green's or the Green's function that have a classical counterpart, which are retarded and advanced Green's functions. Retarded and advanced Green's functions. Okay. Now, let me get things straight here a little bit. We have seen that the definition for the contour Green's function in side basis ij, that's what we call it, side basis, as a function of T and T prime, is minus I over h bar, expectation value of the time order product of Ci of T, Cj of t prime dagger. And then now we will take care of the advanced and the retarded Green's function, which are defined as follows. Cij retarded of t prime is nothing but minus I over h bar theta of t minus t prime. Expectation value of the anti-commutator between ci of t and cj dagger of t prime. Okay, that's the retarded Green's function, and the advanced Green's function is similar, with some sign changes here. So this is I over h bar theta of t prime minus t, sorry, and the same expectation value of the anti-commutator of ci of t and cj dagger of t prime. Okay, now with this and taking into account the quantum dynamics of this operator ci and cj, we will use the definition for the retarded Green's function with a slight change. Okay, so we will not write the Green's function on the ij basis, that is on the side basis, but we will write it on the energy basis. So then, instead of having operators ci and cj dagger that create particles, create or annihilate particles at a given site, we will work on the particle number basis, okay, which tells us that operators cm and cn dagger will create or destroy fermions. Of course, we're talking about fermions at a given quantum state with a definite number of particles. Definite number of particles, that's what is important. Particles, and then we write the Green's function on the what we call on the particle number basis. That's what this basis is called in the following way: Jmn retarded of t prime is equal to minus I over h bar theta of t minus t prime anti-commutator of cmt with n dagger of t prime. And then here what we should let's say think about is the following. So we should think about that in the particle number basis. So in the particle number basis, we have the following rules for quantum dynamics that we derived in the video for Heisenberg equation of motion. So we have that Cm of t is just Cm, which is the operator C in the Schrödinger picture, accompanied by a phase factor given by minus I over h bar. See? Since we are in the particle number basis already, so this is here accompanied by E sub m that represents the energy of the quantum state labeled by m, that's what it is, times t. The same we can say for Cn dagger of t prime, which is just Cn dagger times the phase factor e to the I over h bar ent prime. Okay, so then once we know this, we proceed to replace that here, and then we do the following. So gmn retarded of tt prime is equal to minus I over h bar theta of t minus t prime, expectation value of c m e to the minus I over h bar emt cn dagger e to the I over h bar ent prime. We close the operations there, and then we write minus I over h bar theta of t minus t prime. Since the phase factors are scalars and not operators, I can take them out, and then I'm only left with the expectation value of the anticommutator between cm and cn dagger times e to the minus I over h bar em of t e to the I over h bar en of t prime. Yes, and then we continue. This is nothing but this is just delta mn, so we write minus I over h bar theta of t minus t prime delta mn, which are particle number bases here. And then since we have a delta mn, we can just assume this energy to be the same, and we take it as en equal to em, and then we write the following: e to the minus I over h bar em t minus t prime. Okay, then that's how the Green's function looks like. And then to find to work better with this Green's function, we have to find a spectral representation for the Green's function. That's quite important, and for that we replace the spectral representation for the step function here, theta of t minus t prime, which is equal to minus 1 over 2 pi I integral from minus infinity to infinity of e to the minus I omega t minus t prime d omega divided by omega plus I eta, okay, where eta tends to 0. And then if we replace that expression, what we're left with is the following: we have minus I over h bar, see, times minus 1 divided by 2 pi I integral here of minus infinity to infinity e to the minus omega t minus t prime. Now what we're going to do is that we're going to put this term inside the integral, because this term does not depend on omega, so there's no problem. So then I put times e to the minus I over h bar em t minus t prime d omega, all of this divided by omega plus I eta, see, and all of this times delta mn. We cannot forget that, that's quite crucial here. Now let's continue with this. This is a tedious and long calculation. Well, not so long, but this is just important because the only thing you need to know is what I show you about quantum dynamics in the video about the Heisenberg equation of motion, and you need to know these tricks about complex integrals, and with understanding quite well the Hilbert space and these complex integrals, there's a lot of things that we can calculate, and there's a lot of physics that we can see. So just let's be patient and continue with this. These i's go away, these minuses go away as well, so I am left with 1 over 2 pi h bar integral of minus infinity to plus infinity. So I just factorize things here to make them look like this: minus I, see, over h bar. Then here I have h bar omega plus em t minus t prime d omega delta mn. Everything here goes divided by omega plus I eta, and then what we're left here. So there is a trick that we have to perform at the moment, which is the following. Let's see what happens if we do this. Let's say that we just do this change of variable here, which means that then h bar omega will go to h bar omega minus em. That's what this change of variable will mean. And then d omega will just go to d omega, so there's no problem. And then we write g mn gmn retarded of t prime equal to 1 over 2 pi minus infinity to plus infinity. In this integral we do like this. We have minus I here, omega t minus t prime d omega delta mn, and downstairs we have h bar omega, we have minus em, and we have plus I eta here times h bar. All of these things here I will call it delta because it's sufficiently small, which is what I want. And then I end up with g retarded in basis of mn of t comma t prime equal to 1 over 2 pi, yeah, times the integral minus infinity to plus infinity e to the minus I omega t minus t prime d omega delta mn h bar omega minus em plus I delta. So that this is clearly the Fourier transform of something. So then whatever this is the Fourier transform of is the spectral representation of the retarded Green's function, because gmn retarded of t prime, it will be nothing but 1 over 2 pi minus infinity to plus infinity gmn retarded of omega e to the minus I omega t minus t prime d omega. Okay, so then what we're left with is that the spectral representation for our particle number basis Green's function is nothing but delta mn divided by h bar omega minus em plus I delta. And then one can prove, because delta mn advance of omega is equal to delta mn retarded of omega dagger, that's complex conjugate. Just because we have just a single particle picture here, then this is not a matrix, and so we don't have transposing this complex conjugation, and this is nothing but then delta mn h bar omega minus em minus I delta. So then this is we have now our spectral representation. Good, because this is something that is important. This is not what we want to achieve. We want to achieve something that's called the Lyman representation. That's where we want to go, and the question is, how far are we from that? Well, not so far, but we will not finish that on this video. Something else that I can just mention before we move on to the Lyman representation, we can go to the side basis for the Green's function like this. So we have this representation, this spectral representation will be equal to the summation over mn, see, of some plane wave coefficient here minus I pn dot ri minus rj times jmn retarded of omega. Okay, so what we do here is that since we know by the delta mn that this is a diagonal Green's function, so then we just include here the delta like this, and then we split this here in the following way. We know that the momentum is equal to h bar k, so we write e to the minus I h bar k n dot ri times e to the I h bar k n dot rj. We write times j m m retarded of omega times delta mn. So then one of these indices goes away, and then I write summation over m. So this in quantum mechanics, these plane wave coefficients can be written in terms of bra and ket in the following way. So they are written as the expectation value between state I and state m here, because now this kn becomes this kn becomes km, and this is m here and j, see, and then this is here times j m m retarded of omega. So that's what it looks like, and this will not be nothing but the summation over m of I m mj divided by h bar omega minus em plus I delta, and if you want to put here plus minus to include advance here, then you put here retarded or advance. So then just by some simple analysis we can go from particle number basis to side basis on the Green's function. So particle number basis to side basis. I hope this video will give you an idea of how to work with this object. This is quite important, and on our next video we will target for sure the limit representation of the Green's functions. And for the meantime, this is all, and thank you for watching. Bye.